In Chapter 11, we are going to be building upon the information that we've already learned. We've learned how to write and balance chemical equations, and now we're going to put together that information with the moles that we learned back in Chapter 1, and how to calculate amounts for products or reactants given other amounts. So we're going to talk about multiple conversions, mass-to-mass conversions, limiting reactants, yield, etc., etc. And then we're going to apply those in specific instances, such as aqueous reactions or gases in chemical reactions, and finally talk about chemical reactions and heat very briefly. In chemistry, we have a big word that we use called stoichiometry. Stoichiometry. And it's kind of a scary word for students, but really it just means that we have a numerical relationship between amounts of reactants and products in a balanced chemical reaction. This is a very important concept. We have to start out with a balanced equation. If you don't have a balanced equation, your stoichiometry numbers are not going to be correct. These coefficients that are in front of my molecules in a balanced chemical reaction are molar relationships. So in this reaction over here, I know that 2 moles of carbon monoxide combined with 1 mole of oxygen to give me 2 moles of carbon dioxide. Note that, as always, the missing number here is a 1. That is assumed that it's a 1, and so we don't write it. These relationships are true for any amounts that I start in. So basically, I have a 2-to-1 ratio between a carbon monoxide and oxygen molecules, right? So if I start out with 1 mole of oxygen, I would have to use up 2 moles of CO to give me my product. If I start out with 2, I would have double that. So 2 times 2 is a 1-to-2 ratio or 2-to-1 ratio. We can write conversion factors for any stoichiometry problems by using these molar coefficients in front of these molecules. And we can write them in such a way that we can go in either direction. So we can solve for one or the other. So in this problem over here, right, I have stoichiometric calculations in which I start out with 2 moles of CO, use up 1 mole of oxygen to give me 2 moles of CO2. So if I start with a certain amount, it doesn't necessarily have to be 2 moles, but if I start out with a certain amount of CO and I want to find out how much CO2 I am going to produce, then I can write these conversion factors from these coefficients here, and I can write them in a fraction, just like we've been doing. This way, I can either have 2 moles of CO for every 2 moles of CO2 at the bottom, or I can have those two flipped. 2 moles of CO2 for every 2 moles of CO. So now, depending on where I start and where I want to end up, I would use one or the other of these. So if I start with moles of CO2 and I want to figure out how many moles of CO I needed, right? If I produce, let's say, 4 moles of CO2, how many moles of CO would I start out with to make that much? Then I'd use this one, because then I would have moles of CO2. Always start with the amount you're given in the problem. So 4 moles of CO2 times 2 moles of CO over 2 moles of CO2. This conversion factor here, moles of CO2 would cancel, leaving me with moles of CO. If I start with moles of CO and want to figure out CO2, then I would use this one. So whatever you start with would end up at the bottom of that fraction. What you want to end up with will end up at the top. And then you fill in these coefficients for each molecule. Let's take a look at an actual example. If I start with 3.8 moles of N2O2 in this reaction here, how many moles of NO2 are produced? Okay, so I have N2O2 combining with oxygen to give me NO2. First thing you need to do is double check whether this reaction is balanced. I have 2 nitrogens here. 2 times 1 gives me 2 nitrogens here. My nitrogen is balanced. What about oxygen? I have 2 times 1, even though it's not written, 2 oxygens from this molecule plus 1 times 2, 2 oxygens from this. So a total of 4 oxygens on the left-hand side. 2 times 2 give me 4 on the right-hand side. So I am balanced. Okay, I start out with N2O2 and I want NO2 to end up with NO2. Now, I am starting with moles of reactants and want to end up with moles of product. I write my conversion factor in such a way to get rid of N2O2, which is my starting point, and end up with NO2 because that's what I'm asked. So NO2 will go at the top and N2O2 will go at the bottom of this conversion factor fraction. And then I plug in these numbers that go with each molecule. NO2 has a 2 in front of it, so 2 moles of NO2 goes on top. And 2O2 has 1, even though it's not written, but it's 1, so it will have 1 mole of N2O2 at the bottom. Now this fraction is multiplied by the amount that I start out with, which is 3.8 moles of N2O2. There's my amount that I start with multiplied by the fraction, the conversion factor, where what I want to end up with is on top and what I'm starting with is at the bottom, so that will cancel out. Moles of N2O2 cancel moles of N2O2, and then all I have to do is multiply 3.8 times 2 to give me 7.6 moles of NO2, and that's what I would make if I used up all of that amount. Let's look at an example problem. If I have urea, which is this molecule here, it's a byproduct of protein metabolism. This waste product is formed in the liver, then filtered from the blood and excreted in urine by the kidneys. It can be synthesized in the lab by the combination of ammonia and carbon dioxide, according to this equation. First thing that you're going to do, you guessed it, you're going to have to figure out whether it's balanced or not. And this one is balanced, but go ahead and try it just to make sure that you know how to actually account for whether a reaction is balanced or not. Here's my 2 parts. First, calculate the amount of urea that will be produced by the complete reaction of 5.25 moles of ammonia. Very similar to the problem that we looked at in the previous slide. So I'm starting out with moles of reactant and I want to end up with moles of product. I will start out with the amount that I'm given and then write my conversion factor in such a way that the amount of urea is going to be on top because that's what I'm asked, and the amount of my reactant, which I'm starting at the beginning, will be at the bottom so that it will be canceled out. I will work A for you in the next slide, but B, it says determine the stoichiometric amount of carbon dioxide that is required to react with 5.25 moles of ammonia. I don't have, so basically I don't just use stoichiometry to start from reactant and figure out how much product. I can use it for any molecule here. In fact, for B, we start out with one reactant and we want to know how much of the other reactant we're going to need instead of how much product. The procedure is the same for any molecule here as long as you have a balanced chemical reaction that gives you those coefficients, those numbers in front of each molecule. Let's take a look at A and then you'll have a chance to do B. Here's my reaction where I start out with ammonia and I'm trying to figure out how much urea is produced. Here are my 2 different ways of writing the conversion factors. So I can either write 2 moles of NH3 for every 1 mole of urea, or I can write 1 mole of urea for every 2 moles of NH3. Since I am starting with the moles of NH3, right? This is what's given to me in the problem. So please always start with this amount. Do not start with any other way or any other amount, because you will get confused. Start with this amount that you're given in the problem, which is 5.25 moles of ammonia, and then multiply that number by the correct conversion fraction written in such a way that moles of what you start with will be at the bottom. So moles of NH3 will be at the bottom and moles of urea will be at the top, which is this one right here. So moles of NH3 cancel out, and all you have to do is do 5.25 times 1 divided by 2 to give you 2.63 moles of urea. And now go ahead and work on part B of this problem. Let's work on this other problem as well. This will be a little more difficult for you because in this one, I'm asking you to actually write the reaction and to balance it before you start out with calculating the moles of each reactant. Okay, so this will be a several step problem. First, let's read the problem. You have tetraphosphorus decoxide, this molecule here, reacting with water, H2O, to produce phosphoric acid, H3PO4. So you have these two reactants that produce this product. Write and balance the equation for this reaction and determine the number of moles of each of the reactants. So both P4O10 and H2O that are required to produce to make 5.8 moles of H3PO4. You're going to have to do the calculations twice. So use 5.8 moles of phosphoric acid to calculate how much tetraphosphorus decoxide you need to start with, and use the same amount of phosphoric acid to calculate how many moles of H2O you're going to need.